So Isaac Newton was trying to find an explanation for gravity. Everybody understood that there was gravity and it had effects on a variety of things, including the tides. They also knew by this time that Kepler's laws of planetary motion had replaced the Greek model of the sun-centered universe, the Earth-centered universe, with Copernicus' sun-centered universe. And Kepler came up with three laws. One is all planets move in ellipses with the sun at one focus. So an ellipse is like a flattened circle, and when a circle has one center, an ellipse has two. And in fact, the mathematical definition of an ellipse is all the points, the sum of whose distance from two fixed points adds up to the same. And so if this was an ellipse, this distance plus this distance would be the same as that one plus that one. This one plus that one would be the same as the sum of those two, or the same of the sum of those two. You can put two thumbtacks into a board and loop a piece of string around them and just pull it tight, and you just drag the loop of string around, and that'll make an ellipse. That's the way we used to draw them in the old days before computer graphics came along. So that was the first one. And the second one was all planets sweep out equal areas in equal times. So let me redraw my ellipse here. So the sun is only at one focus, it's at one of the centers. And so if there's a planet and it's here at the 1st of January and it's here at the 1st of February, so it travels from here to here in a month, then the area that's swept out will be the same area that it sweeps out for 2 points a month apart out here. And since these are farther away, for those areas to be the same, these points have to be closer together. And that makes the planet move slower when it's farther away and faster when it's nearer to the sun. It's more obvious in comets, since all the planets are pretty circular in their orbit. We don't see it as much, a little bit, but it's much more easy to see when we follow comets and objects like that. So that was rule 2. This gets translated by Newton later on into the conservation of angular momentum. And the third one is the square of the period is proportional to the cube of the semi-major axis. So the semi-major axis, let me erase again. Draw my ellipse back. Right? Here's the sun. That's the major axis, and this is the semi-major axis. And the period is the time for one lap. So the period is the time to go around once. The square of the period is proportional to the cube of the semi-major axis. And so these three laws, when applied to our planets, suddenly made their motions predictable for the first time ever in thousands of years, since the ancient Greeks had the wrong model. Copernicus in the 1500s came up with the right model, and then Kepler came up with the right mathematics. And so Newton wanted to be able to explain some of this with his law of gravity. It was Newton's idea that rather than just explaining the motions of planets, you ought to be able to come up with a set of physical laws that explain the motion of anything. And we've already seen his first three laws of motion, but he knew that there had to be some law that governed how planets are moved through space. And the name we've given that to that, of course, is gravity. And Newton thought there ought to be some explanation for this force that's gravity that causes these elliptical orbits and causes this behavior that we see in these in terms of the motion of the planets and the shape of their orbits and the time it takes them to orbit. So Newton knew that the acceleration of gravity on Earth is 9.8 meters per second squared. This is the story you've probably heard about, the apple. So he was able to calculate the acceleration of the moon. The moon is just orbiting the Earth in a nearly circular orbit, and so its acceleration is just its centripetal acceleration, which is just v squared over r, or, as we've said in other places, omega squared times r, right? Where omega is the angular velocity of the Earth, of the moon going around the Earth. Omega is omega for the moon, right? Here's the Earth, and here's the moon going around the Earth. This is not to scale, obviously. And so the angular velocity of the moon is 1 lap, which is 2 pi radians over 27.3 days. If we want to convert that into radians per second, which is more convenient, we would say we'd multiply it by 1 day over 24 hours, 1 hour over 60 minutes, 1 minute over 60 seconds, and what we would get is 2.664 times 10 to the minus 6 radians per second. That was the omega, right? And so now we can calculate the acceleration of the moon, and that's omega squared. So it's omega squared times the r, and so this is 2.664 times 10 to the minus 6 radians per second times the distance to the moon, which is 3.84 times 10 to the 8th meters, which they also knew in Newton's time. 3.84 times 10 to the 8th, or they knew it approximately, meters. And when you multiply all that out, you get I'll write it down here. 2.72 times 10 to the minus 3 meters per second squared. And so Newton looked at that and this, and he noticed that if you take the acceleration of gravity divided by the acceleration of the moon, the number was about 3,600. If you took 9.8 meters per second squared, maybe I'll just write it out, 9.8 meters per second squared over 2.72 times 10 to the minus 3 meters per second squared. It's about 3,600. And so Newton surmised that as you get farther and farther away from the Earth, the acceleration of gravity is decreasing and decreasing. And that must mean that the pull of gravity, the gravitational force, decreases the farther and farther you get away. Well, it turns out that the distance to the moon this distance divided by the radius of the Earth, which is, that distance. In other words, the distance from the center of the Earth to where the surface of the Earth, where the acceleration is this, versus the distance to the moon is about 60. And so the distance to the moon divided by the distance to the surface of the Earth from its center squared is about 3,600. Notice this is the moon distance over the Earth distance, and this is the Earth gravity over the moon gravity. And so what he decided was that the force of gravity is proportional to 1 over the distance squared. That is to say, the greater your distance, the weaker your gravity gets as the square of the distance. So that for something near the Earth's surface, it would have this number squared, and for something at the moon, the distance of the moon from the Earth to the moon, it would have this distance squared. And so there would be a factor of 3,600 between these two guys. And so the force of gravity decreases with distance squared, depending on how far away you are. Newton also surmised that the force of gravity must depend on the mass. The bigger the object, they seem to have greater gravity in proportion to their masses. And so what he came up with was, he said the force of gravity is proportional to the mass of one object times the mass of the other object divided by the square of the distance between them. So m1 equals mass of one object, m2 equals mass of second object, r equals distance. You can use d there. People often get confused by r and think it's half the distance. It's not. R is the distance between the two objects. And it's called r because it's often a radius, because like the distance between the star, the sun and the Earth, the distance between the sun and the Earth is the radius of the Earth's orbit. It's not half the distance. The radius of the Earth's orbit is not half the distance between the sun and the Earth. It's exactly the distance between the sun and the Earth. So any direct proportionality can be made into an equal sign by just inserting a constant, an arbitrary constant. And so Newton called the constant capital G, and he said the force of gravity is equal to G times m1 times n2 over the distance between the two objects squared. The value of G wasn't determined until much later because they didn't have enough, they didn't know the mass of the Earth, for example, and so it was hard to determine. So let me just say it this way. For objects, for objects near the Earth's surface, the force of gravity acting on the object is big G times the mass of the Earth times the mass of the object divided by the radius of the Earth squared. It doesn't matter if I hold the object above the surface of the Earth by a mile or a half a mile or 10 feet or a meter or something. because this number is like 4,000 miles. And so as long as I'm fairly close to the Earth's surface, I can just use the radius of the Earth for this, right? And so G is equal to, it was determined as 1791 by Henry Cavendish, I think his name was, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. That's the universal constant of gravitation. And just for the sake of the Earth, the mass of the Earth is 6 times 10 to the 24th kilograms, and the radius of the Earth is equal to 6.37 times 10 to the 6th. Meters. So let me go up to the top here for a second and say, look, the force of gravity, we've already said, is equal to mg. And that means G must equal to big G times the mass of the Earth over the radius of the Earth squared. Well, if you plug all these numbers in, so 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times 6 times 10 to the 24th kilograms, and divide that by 6.37 times 10 to the 6th meters squared, you get 9.8 meters per second squared. And so it's exactly what you expect. This piece, at least near the surface of the Earth, is just 9.8 meters per second squared. It's what it evaluates to. Of course, if you were doing this on the moon, you would have to put the moon's mass here and the moon's radius here, which we'll do in a minute. So if I want to calculate G on the moon, so here's the mass of the moon, here's the radius of the moon. I want to determine little g. G is just gm over r squared. And so this would be g for the moon. And so to evaluate it, we multiply big G, which is our universal constant of gravitation, times the mass of the moon. If you remember, the Earth's mass was 6 times 10 to the 24th. The moon is 7 times 10 to the 22nd. The moon is only a little more than 1% of the mass of the Earth. The Earth is vastly more massive than the moon. If the Earth absorbed the moon, our gravity, we would only change the mass of the Earth by about a little over 1%. Finally, the radius of the moon is about a quarter of the radius of the Earth. It's 1.74 times 10 to the 6 meters, and so gravity on the moon is about 1.62 times, meters per second squared. And so instead of 9.8 like it is on the Earth, it's a much smaller number. So 1.62. So you'd be able to jump really high on the moon. if you can't already. So we can use the Newton's law of universal gravitation to calculate the force between two people each of mass 100 kilograms, 1 meter apart, right? The force of gravity. So here are my two people. Say they're 1 meter apart, right, is g times the mass of one times the mass of the other over r squared, where r is the distance between them. And so this is pretty easy to calculate because I chose easy numbers, and this is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times 100 kilograms times 100 kilograms all over 1 meter squared, right? And so 100 times 100 is 10 to the 4th times 10 to the minus 11 is 10 to the minus 7. And so this is 6.67 times 10 to the minus 7. And now I've got to sort the units out. I have a kilogram and a kilogram that cancels a kilogram squared. And then I have a meter squared in the denominator, which cancels a meter squared. Here, 1 squared is 1. And so this is 6.67 times 10 negative 7 newtons. And that's what the force of gravity is. And so, you know, that's 7/10 millionths of a newton. It's less than a millionth of a newton. This is why when you walk past somebody in the hallway, you don't slam into them. Gravitational forces are really, really small, and so they're only significant when you're near something like a planet or a star or some very large object. And let's say electrical forces are neutral. So, you know, the Earth is basically electrically neutral, and so there are no other forces acting, and so gravity is a big force. When we start talking about electrical forces, you'll see that if we put, you know, a few hundred kilograms of electrons on the moon and the Earth, that repulsion, like charges repel, would actually push the moon out of its orbit. So that's a simple use of the gravitational force equation.